Hello everyone, and welcome to this webinar titled PLC Programming with DSE Controllers. I'm really excited to be here today to discuss this topic and show you guys how to build some really interesting functions with PLCs. For those joining us for the first time, I'll quickly introduce myself. My name is Fayssal Kotob, and I'm an electrical and computer engineer with more than 6 years of experience in the power field. And I'm currently heading the solutions department at Jubaili Brothers UAE. I'm joined today by my colleague DSE Controllers, who will be facilitating your questions and moderating this session. So let's get started. So in today's presentation, we'll be answering the question, what is a PLC? We'll be going over some basic terminology used in PLC programming. I'll also guide you how to download the DSE configuration suite and the advanced PLC editor, which are made available for free by DSE. Once we do so, we'll go over the editor user interface. Going through the toolbar, we'll also explain the functions of the most common tools like the connections, the conditions, actions, and function blocks. Now, we don't have the luxury of covering the entire arrangement of tools because of the time limit. It's impossible to cover everything in a single session. So I'll focus on the most basic tools. Then we'll wrap everything up with some real-life examples, and finally we'll leave some room for questions and answers. So when it comes to questions, as I go through, if you have any questions, please click on the question mark icon in the bottom right corner and type in your question there, and at the end, DSE will display those questions, and hopefully we can answer them. So, what is a PLC? A programmable logic controller, also known as a PLC, is a robust computer-type device used to control equipment, mostly in industrial environments. The programmable logic controller, or the PLC, receives information from connected input devices and sensors. It processes these received data and triggers required outputs based on pre-programmed functions or operations. What we see in the picture here is a DSE 7320 Mark II genset controller. And very few people realize that this controller actually has a built-in PLC into it. I've been to so many project sites where I see the gensets with controllers, fuel transfer pumps with another controller, ATS panels with a third controller. In some cases, some auxiliaries like fans and dampers in the genset room with their own dedicated controller. And for me, when I see this, it's just plenty of wasted processing power. All of these systems can be controlled via a single controller like the DSE 7320, which you see here. Worst case scenario is that you'll have to add some expansion modules for inputs and outputs. So let's see this in more detail. Onto some basic terms, definitions. What is ladder logic? Ladder logic is a graphical PLC programming language which expresses logic operations with symbolic notations. So it's basically graphical. We are not going to have to write any code. Ladder logic is made up of rungs of logic forming what looks like the ladder, and hence the name. If you look at this ladder here, it's made up of two rails, vertical rails, and horizontal rungs. If you compare this to a PLC program, you can see how similar this looks. So we have our vertical rails, also known as power rails, and our horizontal rungs where the program functions are placed. So what's a Boolean? A Boolean is a form of data with only two possible values, true or false, on or off, 0 or 1. It cannot take any other third value. It's either this or that. An MSC stands for multi-set communication. So when you hear me say an MSC link, I'm referring to the link that connects two or more controllers together. Gencom is a DSE map for all Modbus registers. So this is something proprietary to DSE. A ladder rung as I just mentioned, the PLC program is made of ladder rungs. Now, there's two important definitions that you should keep in mind: normally closed and normally open. A normally closed condition is true when the item is inactive, and a normally open condition is true when the item is active. And please do remember those definitions, because I will frequently use them throughout this presentation. SCADA stands for Supervisory Control and Data Acquisition. It's a system used to monitor and control remote equipment. And this is what we'll be using to test and troubleshoot our programs. So how to download the DSE configuration suite and the advanced PLC editor? The first step is to log in to the DeepSea website. Go to your browser, write in deepseaelectronics.com. You need to create an account or register. To do this, it's very intuitive. It's really easy. I'm not going to go through it in detail. They'll ask you for your name, your occupation, your email address. You'll set a password, and there you go. You have a free PLC, a free DeepSea account. Once you're registered, you log in, and you can download the DSE configuration suite for free using the link I've provided in here. And that's it. You're all set to go. Downloading the advanced PLC editor is something optional. You don't really need it to build your PLC programs. But let me just give you an idea of what the advanced PLC editor is. It was developed to be used with the 7.3 series and the 8.6 series. And it also has some additional features like user-defined functions, like some logic gates. It can communicate with other controllers as well. It has some mathematical functions, built-in PID, etc. But for basic applications, you don't really need all those. Just for your information, in this presentation, we'll be using the advanced PLC editor. But if you fully understand those, it can easily be applied in the standard PLC editor. The only difference is in some terms, and I will highlight those as we go. So let's explore the toolbar in the advanced PLC editor. The first 9 icons are typical Windows tools, so I won't be explaining those. You've got your new, open, save, save as, cut, copy, paste, undo, and redo, and I'm sure you all know what these tools do. I'm gonna start with the import PLC. Import PLC imports a saved to disk PLC program, so it's saved to your computer, and adds it to the existing PLC program. It's compatible with new and old programs. Export PLC exports the highlighted portion of the PLC program to disk. So in order to import something, you should have exported something previously. So let's say you have a huge program, and there's some part of this program that you'd like to use in other programs as well. You just highlight it and export it to your computer and have it saved there. The next tool is add label. It adds a line of text to the PLC editor. So this allows description of the PLC function. In small programs, this is not really necessary, but when your program gets big and complicated, I really advise you to use this. This is used for documentation. It tells you what you're actually doing in simple English words. So when you need to modify or troubleshoot your program in future, this will help you to identify what's happening easily. So documentation is really important. We also have defined item usage. This shows a list and the position of currently used virtual inputs, coils, counters, timers, variables, persistent variables, and strings. It makes it easier to find where they are within the PLC program. Now, you might have noticed there's something called variables and persistent variables. The difference between both is that variables are stored in volatile memory, whereas persistent variables are stored in non-volatile memory. Meaning, if the DC power is cut from the controller, if the controller shuts down for loss of power, the persistent variables are still stored in the controller and still hold their values. And this is really important. We also have the show hide line number tools. This turns on and off the PLC line numbers. Virtual inputs. This helps us view and edit the configuration of virtual inputs. We can also see all the variables by clicking on variables. To add, edit coils, counters, persistent variables, timers, strings, and normal variables. The other tool is system device addresses. This helps us view, add, and edit the system device addresses. This is only useful in case you have other external controllers connected to your main controller. Import PLC from module. This is very similar to import PLC, but it imports your PLC program not from your PC or computer, rather than actually it imports it from the module directly. So you have to have your module connected to your laptop once you need to use this tool. Set persistent variables. This helps you view and edit all the persistent variable settings. Only available when the editor is connected to a module. Again, this is same like import PLC from module. You have to have your module connected. Clear pin clears the PLC pin if one is set, and pin sets a pin number that prevents PLC from being displayed and added. So if you have a controller with a built-in and you've developed some PLC program, but you don't want anyone or you don't want your customer to tamper with this PLC program, you can simply set a pin. Connect SCADA. This connects the editor to the connected module and opens SCADA monitoring. And again, you need to have your controller connected to your PC to use this tool. So let's discuss those tools. In tools, we'll be discussing connectors, the most common conditions, and basic actions. I'll cover some interesting functions in the example because we can't go through all of them. So when it comes to connectors, we have internal output and internal input. Let's look at the example for better understanding. So we have a contact here to check if the fuel relay is active. And if either the start relay is active or the generator is available. And notice, please beware that when I'm using the terms and or, I'm referring to logical ands and ors, okay? So when we have the contacts in series, this is a logic and. Whereas if the contacts are in parallel, like these two contacts, this is a logic or. We're also checking if the system is in auto mode. So if the whole sum of these checks return true, this will drive an output rotating in auto. So this part here is telling me that the engine is running, and this part is telling me that the engine is running in auto. Now, if I want to check if the engine is running in a different trunk, so instead of building this entire logic, what I do here is that I place an internal output, and I simply add an internal input on the new rung with the same name. So this will save plenty of time. Now let's check out tools conditions. These are the different conditions we can test for. So we have a contact test. This is to test the state of a contact to determine if it's true or false. True or false, right? So this is a Boolean, as we discussed before. Instrumentation value. This is to test the module's instrumentation value against another value in several ways. Several ways meaning equal, less than, greater than, equal or greater than, etc. Time of day. This tests the module's internal clock for a specific time of day. Example, 10:32 a.m. Now, day of week, day of month, week in month, and month are very similar to time of day. Button test. This tests the state of the module buttons to determine if one is pressed. We also have a sentinel check. It checks that the selected instrument to see if its current state is a sentinel. Pulse output adds a pulse function to the selected coil to change the coil value from true to false at specified intervals. And we also have Gencom status. Checks that the device selected from the system device address is responding to Modbus queries. Let's discuss contact tests in more detail. So a contact is an internal state of the module. So let's see how the contact test works. By the way, if you're using a standard PLC editor, this is called a flag, but it's the same concept. So once we drag this contact test into our editor, we'll have to set its polarity. It's either normally open or normally closed. And we give it a source. In this case, fuel low level alarm. So this is what we're checking. We're checking if the fuel level low alarm is active or not. Now, so if our fuel level low alarm is active, or we have a high coolant temperature warning. So if either of those conditions is true, because this is an OR, you see these contacts are in parallel, and my generator is available, and my fuel relay is true, then sound an alarm. Next is the instrumentation value. So the instrumentation value allows the module's instrumentation to be tested against another instrument or constant. So for example, when we place a new instrumentation value condition in our editor, we'll have to fill in the value of which the parameter we're checking. Then we'll input, so this is value 1. In this case, we're checking engine temperature. Then we'll input value 2, which is the reference value we're comparing against. So in this case, we set value 2 to 100 degrees Celsius. So how does this differ from a contact test? A contact test is either true or false. However, an instrumentation value can be compared against any value, not just two states. So in this example over here, we have 3 contact tests and 1 instrumentation value. So our program is checking the following state. If the fuel level is low, or my engine temperature is greater than 100 degrees Celsius, and the generator is available, and the fuel relay is active, then set a coil or sound an alarm. Time of the day allows the module's time to be tested and allows an action based upon a specific time or time window. So we drag the time of the day from the tools into our editor. We set the polarity. We set the start time, which is 10. By the way, in Deep C, we follow the 20-hour time format. So 10 means 10 a.m. And the duration in this case is 2 hours. So if the internal time of the module is 10 and 2 hours are elapsed, this turns into true. Now let's go quickly over some actions. In actions, we have set coil. Sets the state of a coil to true. The coil remains true when the driving condition is removed, until a reset or toggle action changes it to false. This is useful for remembering that a condition has occurred. A coil is an internal state of the module. I'll explain this further. You will get a better understanding of this once we compare set coil to toggle coil. Reset coil resets the state of a coil to false. The coil remains false when the driving condition is removed, until a set or toggle action changes it to true. This is useful for forgetting that a condition has occurred. Toggle coil toggles the state of a coil upon the driving condition becoming true. If the coil is currently true, it resets to false. If the coil is currently false, it sets it to true. So it's a toggle, it just does the opposite. Drive coil, it drives the state of the coil based on the driving condition. If the driving condition is true, the coil is set to true. If the driving condition is false, then the coil is reset to false. So what's the difference between set coil and drive coil? In set coil, if the driving condition was true, the coil is set and remains set even if the driving condition turns into false. However, in the drive coil, the coil turns true if the driving condition is true. But the moment this driving condition turns into false, the drive coil deactivates or turns into false. I'm sure you'll have a better understanding of this once we do the examples. We also have the mathematical action. So PLC mathematics allows the user to manipulate instrumentation values with mathematical functions, placing values and results into the module's variables or persistent variables for access later either by the PLC itself or via the module's display. Copy allows a value to be copied into a variable or persistent variables. Clock adjusts the internal clock by adding or subtracting 1 hour. We'll have a very nice example with clock adjust. Virtual input, this drives the virtual input based on the driving condition. If the driving condition is true, the virtual input is activated. If the driving condition is false, then the virtual input is deactivated. So a virtual input provides the same functionality as the module digital inputs, but is activated by the PLC program and does not require hard wiring. So this might come in really handy if your digital inputs are fully used. Override Gencom, this allows the PLC program to write the module's various Modbus registers to change their value. For example, the power output requirement. Reset alarm, this action allows the individual alarms to be reset. An alarm can be reset if the condition that generates the alarm is no longer present. Bit shift is a logical shifter of specified values left or right by the specified number of bits. Value selector selects between one of two values based upon the driving condition and copies the value to the specified variable or persistent variable. Select string shows the selected message on the module's display. Gencom reads the value of the specified Gencom register and copies the value to the specified variable or persistent variable. So this is only used when we have more than one controller connected together. I'm going to skip rate of change because this is not available for all controllers in the advanced PLC editor. So I'm going to cover set coil and reset coil in a single slide because they are relatively the same. So once we drag a set coil into our editor, we have to select coil, which is, in this case, for example, fuel level low. A set coil is denoted by two parentheses with an S in the middle. So if you look at the example here, we have the fuel level. This is an instrumentation test, right? This is similar to the instrumentation value. So we're comparing it to a certain number. So once my fuel level is below 10%, set the coil fuel level low. Now, what happens if this coil fuel level low is set and my fuel level rises beyond 10%, goes to 15 or 20%? This test here will turn false. However, my fuel level low coil remains active. This is the main difference between set coil and drive coil. If I were using a drive coil here, which is represented by parentheses and a D in the middle, the moment my fuel level rises beyond 10%, my fuel level low is deactivated. So I hope this is clear. So whenever we set a coil, we always need to think about resetting this coil. Otherwise, it will be set forever. We need some function to reset the same. So once this is set, we can't leave it set forever. So we need to create a new condition that resets the fuel level low. So we've added another instrumentation comparator here. So I'm comparing my fuel level to the value 80%, and I'm telling this logic gate that if the fuel level exceeds 80%, turn to true, and thus reset my coil. The toggle is quite similar. However, we don't know what the end result is. It's based whether if it were initially false, then the output toggles to true, and vice versa. If it's true, it toggles to false. So we have a very simple example here. We have a toggle coil, and the coil is used to flash an LED. We have a digital input A, so this could be a push button, and each press of the button would switch the toggle on and off. It's very simple. So if I press the button, this LED starts flashing. If I press the same button again, it stops flashing. Drive coil, I believe you are now fully aware what drive coil does. So let's use the same fuel level low example. So if my fuel level is low, I'd like to flash an LED. So if I was using a set coil in this example, what would happen? My fuel level is low, the LED will start flashing. Even if my fuel level rises beyond low, so even if fuel level low turns false, my LED will remain flashing. That's why we use a drive coil in this case. This means whenever the fuel level rises beyond this low fuel level, my LED will stop flashing. We also have some mathematical actions. These mathematical actions allows mathematical functions to be performed, and the results placed in variables, typical variables, or persistent variables. So what are these mathematical functions that are made available in the advanced PLC editor? So there's addition, simple addition, value 1 plus value 2. There's subtraction, again, value 1 minus value 2. Multiplication, division, remainder, magnitude. Magnitude means like absolute value. So it always returns the positive value of any integer. Minimum is the lowest of values 1 and 2. We can add up to 8 values and it gives us the minimum. Maximum gives us the highest value. The average also gives us the average of the values entered. For example, if you have value 1 equals to 6, value 2 equals to 4, your average is 5. And note here that the remainder is lost. If your average has a remainder, it's lost. Range. A range is the difference between the maximum and the minimum of two entered values. For example, if your value 1 is 5 and your value 2 is 7, your range is 2. Bitwise AND and bitwise OR. This is if you're adding or subtracting binary numbers and zeros and ones. So let's have a quick example in mathematical functions. So the below example shows a mathematical operation to find the average of 3 alternator winding temperatures. And this is what we do typically when we try to monitor the alternator winding temperature. You've got 3 main coils. This means you've got 3 temperature sensors, each giving you a different reading. So what is your winding temperature? Typically speaking, it's the average of all 3. So this function comes really handy in such situations. So the operation selected is average. The number of values 3. Value 1 is coming from an expansion module. input A, value 2 is coming from an expansion module, input B, value 3 is coming from an expansion module, input C. Okay, this is assuming that we are using a separate expansion module. However, you can use the existing analog inputs on the controller itself. And your target is the average temperature. So this mathematical function will calculate the average and write this value into the target. Now, before going into the examples, this is a very important note. It is the responsibility of the PLC programmer to ensure that the PLC program operates exactly as intended. DeepC cannot be held responsible for any issues arising from unintended actions of the PLC program. Why are we saying this? You see, typically speaking, you can create an amazing program with no errors, but that doesn't mean that it will do the intended functions, the functions you are planning for this program to do. For example, someone can write a code, compile it, the compiler returns 0 errors, but that doesn't really mean that the function or the program works as it should. So the main point to remember with the PLC is that the designer is not changing existing functions within the module. They are using them in different ways to help ensure that DSE's high level of protection and safety cannot be bypassed with the PLC. However, great care must still be taken to ensure the PLC program operates as required by the designer. So please, if you're working with the PLC editor, trying to build some function, and you're not sure what you're doing, you can always come back to us. We can have a session. We can go through this PLC program together, discuss it, and see if it works or performs the intended function or not. Now, let's jump into the examples. We're going to have 2 examples today. The first one is an auto clock adjustment for daylight saving. So our problem here, we'll start with the problem definition, is that we need 1 hour to be added or subtracted from the module's internal clock automatically to adjust for daylight saving. So whenever daylight saving happens, clocks are edited. We don't want to go to our controller, connect it to our laptop, and change this clock manually. So this can be easily performed using the time clock function. I'm gonna stop my presentation for a minute and open the PLC editor. Before we go into the example, I'm just gonna show you the difference between the standard PLC editor and the advanced PLC editor really quick. So I have a 7320 module here. I'm gonna exit that. I'm gonna open a 6110 module, and this is my 6110 MK3. I'm not gonna save any changes. Okay, there we go. So to open the basic PLC editor, all we do is that we go to Advanced. Under Advanced, there's a PLC tab, and we press on PLC Logic. And this here is my PLC editor. You cannot open the advanced PLC editor with a 6110 module. So let's go back and select our 7320 module. This is our 7320 module. It's loading. Okay, there we go. So if I go to advanced here, I go to PLC, I see this. Once I press this, it will open my advanced PLC editor. There we go. Okay. So just to save time, I've already built this function. So I'm going to open it and we'll go through it in detail. So I'm going to open. I have my DST file here. And there we go. By the way, each project has a name, has a version, and a description. So let's describe this. So let's say this program helps changing the internal clock. Okay. So, and as you can see, I've added some labels here. This is plus 1 hour and minus 1 hour. So what does this program do? First of all, before going into the DST instrumentation value, when it's the last Sunday in the last week of March, I want to increment my internal clock by 1 hour. So what I've done here is that we drag and drop. I'm gonna do this again just for you to see, guys, how this was built. So I'm gonna come here to day of week. I'm gonna drag it and drop it in my PLC editor. I'll select it. It's a normally open condition. So I'll go to days. I'll say Sunday. Then I'll go to week in a month. I'll put it in series because I need an AND function. I want to make sure that when it's Sunday and it's the last week of March and it's March, the last week of the month and it's March, and the time is as such, I'm gonna drive certain coils. So let's see how this happens. So I'm gonna select my week. I'm gonna say it's the last week of the month. Then I'm going to add a month. I'm gonna say that this is happening in March. And I'm gonna check the specific time of the day. Let's say it's 1 a.m. Remember the 20-hour, 24-hour format. And 1 minute duration. I want to do something here. So when this happens, I'll go to the functions. I'm sorry, to the actions, and I'm gonna put a clock adjust action here. And I'm gonna say I have two options. It's plus 1 hour or minus 1 hour, and I'm gonna say plus 1 hour. So if I stop here, if I just do this, what's gonna happen? On this specific time and specific day, so when this occurs, when the whole sum of this is true, when it's 1 a.m., when it's March, when it's the last week of March, when it's on a Sunday, I want my internal clock to add 1 hour. There you go. The system works. The function works. But what happens next year? The thing is, this will keep on adding 1 hour, 1 hour, 1 hour every year. So I want to make sure I'm not just adding 1 hour. There's a certain state or a certain time where I need to decrease or reduce my timing by 1 hour. So let's do this. Again, I'm gonna put a day of the week in a month, I'm gonna put the month, I'm gonna put the specific time, and I'm gonna put a clock adjust here with minus 1 hour. And this is, let's say, a Sunday. This is last week. And probably decreasing the time is happening in October. It doesn't happen the same month. Okay. Am I missing something? Yes, I am. Okay. So for me to start, or for the controller or the PLC to start reading this line, I should know where am I standing. Am I in the winter timing or in the summer timing? That's why we've added an instrumentation value here. Okay. So I have this instrumentation value, which is zero in case I'm in summer timing and 1 in case I'm in winter timing. So what I'm gonna use here is a condition. Here's my instrumentation value. I'm gonna take it, I'm gonna put it here. This is my instrumentation value, okay? Value 1, it's a persistent variable because I need this to be installed in my module even if the DC power is cut. So I've already created this variable and I've called it DST for daylight saving. I'm gonna put it here. I'm gonna test it against, so if it's equal to, I'm gonna test it against a fixed value, in this case 0, keep it as such. Now what I want to happen, if it's 0 and we are in the specific timing of this year, I'm gonna add 1 hour to my clock and I'm gonna write 1 into this persistent variable. So I'm gonna use the copy action. So I'm gonna do this and I'm gonna choose my value. So it's a fixed value, it's equal to 1. And I'm gonna write it into my DST persistent variable. Makes sense? I hope it does. Again, we'll do the same thing with decreasing 1 hour. So I'm gonna do this only if my DST is equal to 1. So it happens right after this. So I'm gonna put an instrumentation value here. And I'm gonna put this. So this is equal. And the value here is a persistent variable, so my DST equal to a fixed value. This value is 1. Okay, and I'm gonna copy 0 into this after the function is executed. So I'm gonna put my value as 0, and I'm gonna copy it to my persistent variable DST. I hope this is clear. I hope you can see how this was built. Okay, so this function is covered, this example is covered. Let's have a look at another example. I'm gonna go back to my presentation. And here's a very interesting example. Okay, auto fuel filling system. Before we go into the DSE or the PLC editor, let's have a look at this diagram and try to understand what's happening and describe what kind of function are we looking for. So we have a bulk tank, a bulk fuel tank. We have our daily fuel tank. Each of those tanks has 2 switches for fuel level, low and high. I've denoted them here with L1 and H1 for the bulk tank and L2 and H2 for the daily tank. We also have a fuel transfer pump. We have our DSE 7320 controller. And we have 2 alarms, one for bulk high and one for daily low. So everything in black is an input to my DSE controller and everything in red is an output. Now I'm sure you all know that you can't just simply connect the DSE controller to a pump. There should be a contactor here to interface with the transfer pump since it's a high power machine. But this is just for illustration purposes. So what kind of scenarios might occur and what is the desired outcome of the PLC program we're going to build? So if I have some fuel in my bulk tank and my daily tank is below the low level, so my low is inactive. I want this transfer pump to run, filling fuel in the daily tank. Now, as I'm saying this, I'm thinking in the back of my mind about my PLC program and how will we translate these English words into a PLC program. So I want my transfer pump to run if this is inactive. But what about the moment this fuel rises above L2? This becomes active. Should I stop my pump? No, I shouldn't. This tells me that I cannot use a drive coil. I need to use a set coil. You see the importance between set coil and drive coils? So this pump will keep on running, fuel will keep on filling, and when should I stop this transfer pump? There are two conditions where this transfer pump should stop. One, if I reach H2, so my daily tank is full. The other condition is that if my bulk tank goes below L1, then I should also stop the transfer pump, because this means I'm out of fuel in the bulk tank. We also have two alarms, one for bulk high. So whenever, because practically speaking, we might be filling this bulk tank manually. So I need some alarm to tell the operator, stop filling, you've already reached high. And again, I'm thinking how to do this in a PLC. So let's say H1 is active and my bulk high alarm goes on. It will keep buzzing until the fuel level drops below H1. So I should put some kind of timer. Let's say be active for 20 seconds, and we'll see how to do that. There's another alarm here for low level in the daily tank. Now, I don't want this alarm to be driven as a set coil, because the moment my fuel rises above L2, I want this alarm to shut off. So I'm going to use a drive coil for this. Let's have a look at the PLC program. I'm going to open a new one. I'm not going to save this. This is my fuel pump, already built it. And let's see how this goes. Okay. So let's put the alarms aside. Let's think about the pump for the time being. By the way, just for your information, definitely we'll have to name this program, make a description, put some labels. But just for your information, the coils I'm using here, the contact tests I'm using here in this PLC program, I've done some variables and gave them meaningful names for your understanding, for just to make it clear for understanding. But in a real life situation, these coils are connected to level switches, physical level switches in the tank. So typically speaking, these would be assigned to digital inputs on the DSE controller. Let me show you how this is done really quick. Okay, so I have this contact test. The source is now a coil variable. But what I'd actually do is that I'll change the source to a control. I'll go to status. Control generator status. Hold on just a minute. It should show us the PLC here. So these are the variables that I have identified earlier, H1, H2, L2, just to make it easier for you. But we have to go to control, generator, and we'll select the digital output inputs, sorry, here module, digital input. For example, let me say it's a digital input D. If I select digital input D, it turns into a digital input D, but this wouldn't be very meaningful for you guys. So I just use variables to make it easier for understanding. And this means that if I go back to my controller here, I make sure that my digital input digital input D is connected to my physical fuel level switch. Okay, so let's go back to the editor. I'm going to undo, and this is coil L1. So if my coil L1 is active and coil L2 is not active, then start a pump. And this is a set here because I want my pump to keep on running until I reach a stop or a reset condition. So this tells me, if this is true, this tells me that the bulk tank has some fuel in it. It has some fuel above the low level, which is good. Then it means that we can start our pump. And this tells me that the fuel level in the daily tank is below my low switch. That's why it's a normally closed condition. So in this case, I need to start the pump and sound the alarm. See the difference between these coils? Start pump is a set coil. Sound alarm is a drive coil. Because the moment my fuel rises above the low level, I want my alarm to stop. But I don't want my pump to stop running. When will I stop my pump? So at some point I need to reset this value here. If I reach the high level in my daily tank, so if H2 is true, it means my fuel level has reached the high level in the daily tank, or my low level in the bulk tank is false, that's why it's a normally closed contact in this case, then start pump is reset. Then this variable, which is start pump, is reset. It's turned into false. So this covers the fuel transfer operation. Now, let's go into the alarms. I have two alarms, right? One is already covered here. We already programmed the daily low alarm. Now let's think about the bulk high. So as I just mentioned, we need this alarm to run for some time, some specific period of time, and then shut off. So how do we do this? If my H1 switch is active, that means my fuel level exceeded the high level switch in the bulk tank, then I'm feeding this into a counter, and I'll explain why are we using a counter here. So CU in a counter is count up, and this only happens on the rising edge of the condition being tested here. I've limited this counter to 1. So if this counter reaches 1, the output is true. So we have a coil, our fuel level is high, the counter goes up by 1, we've reached the limit maximum, the output is true, it will sound alarm bulk tank high. So this will keep on running. Typically, if I leave this as it is right now, it keeps on running. The alarm will never shut down unless we reset this counter. So I need something to reset this counter. That's why I've added a timer here, a timer that goes on for 20 seconds. So the timer is dragged from the functions here. So I have dragged a timer on. This is your timer. Okay. Then we configure it. We set a delay. Elapsed time is optional. You don't have to see it, but if set, then you can see the elapsed time here, and save it into some kind of variable, but that's not needed for the example. Watch, by the way, with many functions or actions, if you see a watch, it means that this certain variable or this certain status can be displayed on the DSE controller. So what have we done here? We've put the alarm for 20 seconds, the delay for 20 seconds, and my driving condition is that the coil H1 is true, it's active. My fuel has reached the maximum high level. This will help me reset my timer and thus shut off my alarm or reset my alarm. This here is what is a drive coil, not a set coil. That's why, so whenever this part of the function turns false, this will turn off my alarm. And that's it. So once we've built our PLC program, it's really important to test and troubleshoot. And to do so, it's really good to use the SCADA functionality provided by PLC. Let me quickly demonstrate this. Just go back to the presentation. Okay, so we finished this example. So we have a diagnostics monitor. To aid the fault finding process. So we press this icon. Once it shows that the module is connected, we can run SCADA. So you have to have your module connected to the PC to do this. And it will show you a real-time operation of your program. So analog values are displayed in real time, like the battery voltage here. Counters, you can see that the counter is counting from 0 to 1 to 2, etc. Conditions highlighted in green like these are active or true conditions. So you can see exactly what's happening real time. If you look at the outputs, if it says clear, it means that the coil is not set. If it says set, it means that the coil is already set. With timers, you can see elapsed time live. You can see how the timer is working. And this is really, really important for troubleshooting and diagnostics. So once you've built your program, always connect your controller, open the SCADA, and run it to see what's going on. This will help you fix any mistakes that you might have done during development. Thank you so much for your time. I really hope you enjoyed this. And let's hop into the questions. I'm going to stop sharing here. Daisy, can you start with the questions? Question, does the DSE controller work with all generators? Yes, it does, of course. You're most welcome, gentlemen. Thank you. The answer to this is yes. We can do PLC programming for synchronization panel. Yes, you can. Absolutely. Guys, once I share this material, go through it. If you have any questions, please feel free to contact me anytime. Daisy is going to share my contact details. You can drop me an email anytime. And if you need any assistance or support, we can make a one-on-one session. That's totally fine. PLC for load reserve start stop. It is doable. Yes. We'd like a training of synchronizing the DSE 8610. We'll plan on that. No worries. Which modules have PLC functionality? I can send you a detailed list, but basically your 6110 Mark III, your 7320 Mark II, your 8610 Mark I and II. But I can send you a detailed list because some other controllers that are not related to gensets do have these functionalities. You have some ATS controllers with PLC built into them. You have an engine controller, the E400 also supports a PLC. How many alternator winding RTD can be connected in DSE 7320? As much as you want, as long as you don't exceed your analog inputs. Because your RTD is connected to the analog input. Habib is asking, and temperature derating functions. What do you mean by temperature derating functions? We can do PLC programming for synchronization panel from 𝐂𝐧𝐭𝐚. Yes, the answer is yes. Habib, if I understood your question, you mean to limit the output based on ambient temperature, right? If we can do that automatically. The answer is yes, we can do that automatically. We can have a temperature sensor measuring the ambient temperature, and based on that ambient temperature, we can limit our generator output in order not to exceed the derated values. Yes, it is possible with PLCs. DSE 7320 is suitable for offshore environment. Yes, it is. I can send you the data sheet that shows all the controller specs in terms of IP, UV index tolerance, vibration tolerance, etc. Does the climate change affect the system? It does not affect the DeepC program. But climate change can affect your generator output, but it will never affect the DeepC program. Any more questions? Okay, I think we're good to go. Thank you so much for your time. Thank you for attending, and hopefully we'll meet you in the next webinar.